Pre-training. Birth of a giant. Behind every token you receive from an API stands a factory worth $100 million. 16,000 processors working in sync, a breakdown every 3 hours. And the mathematical formula driving the entire machinery hasn't changed since 2018. Today, we're walking inside that factory. We'll see every station, from the assembly line through quality control to the monitoring dashboard. We'll examine the production bill and find out why this factory explodes hundreds of times before it produces anything useful. By the end, we'll understand what we actually get after spending $100 million, and why 99.99% of teams shouldn't try building their own factory. Let's go inside. First station, the assembly line. The assembly line. Next token prediction. All of pre-training comes down to one goal: predict the next token. The model receives a sequence of tokens and must guess what comes next. Formally, maximize the probability of the next token given the preceding tokens. That same goal has applied from GPT-1 with its 117 million parameters in 2018 to LLaMA 3 with 405 billion parameters in 2024. 6 years, over 3,000 times more parameters, 0 changes to the mechanism. The elegance lies in the labels. Nobody has to manually annotate data. The next token in the text is the label. The internet itself becomes training material. Every sentence, every line of code, every forum post is a quality control checkpoint on the assembly line. During training, the model uses a technique called teacher forcing. At each step, the network receives the correct history from the training corpus and predicts the next token. This allows all positions in a sequence to be processed in parallel. That parallelism is precisely what makes training on trillions of tokens possible at all. Andrej Karpathy put it well. LLMs have little to do with language. A better name would be autoregressive transformers. Tokens don't have to represent text. They can just as easily be fragments of images, audio, or molecular sequences. For practitioners, this is the key insight. Every API call to GPT-4, Claude, or Gemini triggers the same mechanism. Understanding NTP explains why the model completes sentences with impressive accuracy but loses its footing in multi-step planning. Its decision horizon is one token ahead. The assembly line produces predictions. At the end of the line, a ruthless quality control engineer is waiting. Quality control. Cross-Entropy Loss. Cross-Entropy Loss is the mathematical heart of pre-training. The entire formula is one line. Loss equals negative log of p, where p is the probability assigned to the correct token. This simple function hides a brutal mechanism. The process unfolds in 3 steps. First, the network's final layer emits logits, raw numbers for every token in the vocabulary, typically ranging from 32,000 to 200,000 entries. Then, the softmax function normalizes these values into a probability distribution. Every value becomes positive, and the sum equals exactly 1. Finally, the system takes the negative logarithm of the probability assigned to the correct token. That's the loss. The intuition behind punishing arrogance is critical. If the model gives 99% probability to the correct token, the loss is close to 0. But if the model gives the correct token only a 0.1% chance, the loss explodes to 6.9. The logarithmic function tolerates honest uncertainty. It brutally punishes confidence when a mistake is being made. It's like a boss who tolerates mistakes but can't stand arrogance. The elegance of the gradient deserves attention. The derivative of cross-entropy with respect to the logits simplifies to the form p minus y. The error propagated back through the network is directly proportional to how wrong the model was. Softmax and the logarithm cancel each other out, leaving a clean training signal. That's one reason this combination became the foundation of the industry. There's also a deeper connection to Claude Shannon's information theory. The expression negative log of p is the mathematical notation for surprise. An obvious event carries no new information. A rare event is an explosion of bits. When the model is 99.9% certain about one token, and something entirely different appears in the data, the loss function explodes. It forces drastic reprogramming of the parameters. We now know what the factory produces and how it checks quality. Here's how we monitor the entire process at a glance. The monitoring dashboard. Perplexity. Every factory has a monitoring dashboard. In pre-training, that role is played by Perplexity. The formula is straightforward. PPL equals E raised to the power of loss. Intuitively, Perplexity tells you how many options the model is considering at each step. Perplexity 50 means the model is as lost as if it had to choose uniformly among 50 options. Perplexity 2 is a coin flip. The scale of progress is staggering. At the start of training, Perplexity sits near 48,700. The model is practically lost across the entire vocabulary. After training, the best models reach Perplexity below 2. GPT-2 XL with 1,500,000,000 parameters achieved Perplexity of 18.34 on the Wikitext-2 benchmark. GPT-3 with 175 billion parameters, Perplexity 1.92 on Lambda in few-shot mode. From 48,000 to under 2. That's the transition from total chaos to near-surgical precision. The key insight: the curve never becomes completely flat. LLaMA 3, trained on 15 trillion tokens, was still learning. Mark Zuckerberg confirmed it. The 70B model was still improving even at the end of 15 trillion tokens of training. Databricks trained 47 models and found no saturation point. Models are therefore systematically undertrained, not because data or patience is lacking, because continuing training becomes brutally expensive. A drop in cross-entropy from 3.4 to 2.8 can require 10 times more training data. The curve keeps falling. The reason we stop training: money runs out faster than data does. The factory bill, costs and scale. How much does a factory like this cost? The cost trajectory of pre-training is one of the steepest exponential curves in the history of technology. The original transformer from 2017 cost roughly $930. GPT-3 in 2020, an estimated $4 to $12 million. GPT-4 in 2023, over 100 million. Sam Altman confirmed that publicly. Growth of more than 100,000 times in 6 years. The cost structure reveals a surprising breakdown. According to Epoch AI analysis, hardware accounts for 47 to 65% of total cost. Research staff, including equity, accounts for 29 to 49%, and electricity just 2 to 6%. That's right, energy is a surprisingly small component. The real cost is silicon and the people who know what to do with it. The comparison between LLaMA 3.1 and DeepSeek v3 exposes a paradigmatic difference in cost engineering. LLaMA 3.1, brute force approach, 16,000 H100 chips, 54 days, 30.8 million GPU hours. Estimated cost over $100 million. Every token activates the full 405 billion parameters. DeepSeek v3, lean manufacturing, 2048 H800 chips, 55 days, 2.79 million GPU hours, $5.6 million of compute alone. The difference? 12 times fewer GPU hours for comparable quality. DeepSeek's secret lies in its mixture of experts architecture. For each token, only 37 of 671 billion parameters are activated. On top of that, FP8 mixed precision, the first open model trained at that precision. custom CUDA kernels achieving over 85% GPU utilization compared to the industry average of 55 to 65%. An important caveat about hidden costs. Semi-analysis revealed that the declared $5.6 million covers compute alone. DeepSeek's total hardware investment exceeds $500 million across the company's entire history. Research costs, iteration cycles, and staff are not included. Both numbers are true, they simply measure different things. $100 million spent, 16,000 GPUs working in sync, and then one processor dies, and the entire factory stops. Explosions on the production line. Loss spikes. 100 million spent, and then the line explodes. Loss spikes are sudden surges in loss values that threaten months of work. Left unchecked, non-value propagation, irreversible weight degradation, catastrophic losses. At sufficient scale, GPU systems fail almost continuously. If a single H100 breaks down once every 50,000 hours, a cluster of 100,000 GPUs has a breakdown every 30 minutes. 1 million GPUs every 3 minutes. Palm experienced 20 loss spikes despite gradient clipping being enabled. Spikes appeared at irregular intervals, sometimes late in training. The key insight from Google's report: spikes occurred through a combination of specific data batches and a particular model parameter state. Replaying the same batches from an earlier checkpoint did not cause spikes. It wasn't bad data. It wasn't a bad model state. It was their unpredictable collision. Opt 175B is a case of unprecedented transparency. Meta published roughly 100 pages of raw training logs. At least 35 manual restarts, around 70 automatic ones, over 100 in total. They switched between optimizers. Hardware failures became routine. Several machines went down every day. Now a case study that shifts the perspective entirely. LLaMA 3.1, 54 days of pre-training on 16,384 H100 chips. Meta's cluster suffered 419 fatal hardware failures, one every 3 hours. Nearly 47% of failures came from GPU and HBM3 memory defects combined. GPUs accounting for 30%, HBM3 memory for 17%. If even one of those 16,000 processors dies, the entire FSDP architecture halts until it's reloaded from a checkpoint. Despite all this, over 90% effective training time. Meta's team built their own diagnostic tools and automatic resumption mechanisms that kept production running at an absurdly high level despite permanent hardware chaos. The contrast is DeepSeek v3, 14.8 trillion tokens in FP8 format. Not one irreversible spike. 0 rollbacks. That's the new reliability standard for the industry. 419 failures, over 100 restarts, millions of dollars. Here's what we get at the end of that process. The final product, base model. The factory has produced its final product. What exactly is it? After pre-training, the model is a masterful text completer. It's not an assistant though. The base model handles document continuation. It can continue a sentence with accuracy that commands respect. It performs poorly, however, at instruction-following tasks, like fix the grammar or answer yes or no. It doesn't understand the contract of task-based work or user expectations. The proportions are telling. Pre-training consumes 98% of total compute resources. Post-training, supervised fine-tuning, and RLHF is a small fraction of that compute. That fraction changes everything in the user experience. As Karpathy put it, in SFT, you simply swap documents for curated conversations and continue training. Algorithmically, nothing changes. the user experience changes completely. The practical conclusion is unambiguous. A cost exceeding $100 million, the required expertise, the risk of 419 failures over 54 days. 99.99% of teams should not train their own models. For most organizations, the rational strategy is to use existing models and fine-tune on their own data. Let's return to our factory. Behind every LLM stands a factory that survived hundreds of failures. It's not the magic of the algorithm. It's the craftsman's triumph of engineering. If you want to see how this base model becomes an assistant, subscribe to the channel. Next episode, supervised fine-tuning, teaching the model to answer questions. Thank you for watching.